Welcome to the fourth and final presentation in Unit 4 entitled Total Recoil. It says one cannot violate the promptings of one's nature without having the nature recoil upon itself. Jack London. So the goals for this particular presentation are that you be able to describe momentum as a conserved quantity in explosions, that you be able to determine the momentum of an object before and after an explosion, and using this particular equation, which we now know is the conservation of momentum equation. So here's what we already know. We know momentum is a product of mass and velocity. We know that mass is conserved in a closed and isolated system, and we know that collisions are examples of closed system mechanics. So, here's what we learned in the lab. Conservation of momentum occurs in explosions as well. And we saw that whenever we saw the watermelon explode. The momentum of the watermelon was zero before, and because we have particles going in the opposite direction in a spherical pattern, this chunk right here is canceled by this chunk, and this chunk right here is canceled by this chunk, and so on and so on and so on. But the total momentum ends up being that same zero value. So like we said before, momentum is conserved in a closed isolated system, which means that there is no friction. So we can say friction, and then we put an X on it, and that the total momentum is the same before and after. Now an explosion is a situation in which generally the total momentum before is zero. So you usually have some sort of stationary object, and so you have a momentum of zero because the velocity is zero. Then what you do is you explode, and you're giving one thing a positive momentum, say plus 100, and then you have something else moving in the opposite direction. Remember, because momentum is a vector, it's important to know what the direction is, because if this is a positive 100, this is a minus 100, and it would add up to that original value of 0. So we've already looked at the conservation of momentum equation. There's nothing new here. We're talking about mass, velocity, and then the object, whether it's object 1 or object 2, and then you have before the collision, and then you have after the collision or explosion. So it says, what is the system in which momentum is conserved when the soda bottle explodes? And the system would include not only the bottle, but also the liquid. And you can see that while you see the liquid moving off in all directions. And you see parts of the glass moving off in all directions. So it says, what is the total momentum before and after a collision? It's actually an explosion when a cannon is fired. So whenever you see this right here, before a cannon is fired, it has a total momentum of 0. And the reason for that is the cannonball is actually at rest in the cannon, and the cannon's not moving. Now, whenever the cannonball is fired, you're giving it a positive velocity or a positive momentum, but the cannon actually moves backwards, and so it has a negative momentum. If you were to take these two momentums and combine them, the law of conservation of momentum says that they have to equal 0. So it says the roller skater shown below initially travels at a constant speed to the right. She trips. In order to regain her balance, she throws her trays forward. What will happen to her velocity? So she has some sort of momentum going this way. By taking this particular trays and throwing them forward, she's actually given the trays momentum. Well, what that's going to do is that's actually going to reduce her own velocity, because this and this have to combine to be the original value. You can see this very easily, not in this particular case, we don't want you to trip on roller skates, but if you've ever been on a rolly chair, okay, if you've ever been on a rolly chair and you push off a wall, well, if you exert a force forward, the wall actually pushes you backward. Now, we talked about that a little bit when we talked about Newton's third law. Finally, it says a 5 kilogram rock initially at rest. Here's my 5 kilogram rock. It's a nice hexagonal rock. Explodes, sending 2 fragments to the left and 1 to the right as shown. What is the velocity of the fragment moving to the right? So this is a particularly difficult question. Okay, so the first thing I would say is that the momentum total has to equal 0. And the reason why is the rock is initially motionless. Now I know that I have 2 rocks moving to the left, and I have 1 rock moving to the right. So if I look at my rocks that are moving to the left, the first one has a momentum of 1.25 times 40. That's the momentum of the first fragment. When you multiply that out, 40 times 1.25 ends up being a momentum of 50. The 100, or the smaller fragment right here, is going to end up having a momentum of 75. So I have two fragments that are both moving to the left and have a total momentum of 125. So what that means is that the momentum to the right has to have 125 so that it adds up to that initial value of 0. So because of that, I know the momentum of this larger rock is going to be 125. And that's going to equal the mass times the velocity. And even though it doesn't say, you can figure out the mass of this particular chunk based on the fact that the original rock was 5, and then the first fragment is 1.25, and the second fragment is 0.75. So that means the fragments that move to the left are 2, leaving you a 3 kilogram fragment that's moving to the right. So you have 125 divided by 3 would allow you to solve for the velocity, which ends up being about 41.7 meters per second. And that is, of course, meters per second to the right.